He is assistant professor at the Department of Medical and Nanotechnology, Tehran University of Medical Science, Iran. And his research area and expertise is targeted drug delivery, nanomedicine, uh, blood-brain barrier, magnetic nanoparticles. Okay, without further ado, now I'll invite Dr. Nasrollah to deliver the lecture to Dr. Nasrollah Tabatabaei. The time is yours.
Hello, everyone. Thank you. Thank you for that nice introduction. How do I share my screen?
Yes, you can share your screen now.
Okay. Give me 1 second. Let me see. Hold on a second. I'm having trouble with sharing my screen.
Okay, please take your time.
All right, I think it works. Do you see my screen now?
Yes, I can see your screen.
Okay, good. All right, thank you for this very nice introduction. Hello, everyone, and thank you for being here. My name is Nasrollah Tabatabaei, and I'm a faculty member at the Department of Medical Nanotechnology at Tehran University of Medical Sciences in Iran. We have, in fact, a wonderful student from Indonesia here in our department, and I'm happy to be here with you. So the topic that that I'm going to talk about today is related to magnetic nanoparticles and their applications, their biomedical application. This is a very introductory topic, and I don't go too much into details. It's just to let you know what's available. So. All right, so magnetism is a property of a material that respond to an applied magnetic field. Permanent magnets, such as the one you see in this image, have persistent magnetic fields caused by ferromagnetic. We're going to talk about a little later. But all materials are influenced differently by the presence of a magnetic field. Some are attracted by the magnetic field, like paramagnetics. We will talk about them as well. And others are repulsed by it, like diamagnetics. Still others have a much more complex relationship with an applied magnetic field. Substances that are little affected by the magnetic field are considered non-magnetic, and there are like examples of those could be copper, aluminum, and maybe some gases and plastic. But for example, pure oxygen and in a liquefied state exhibits magnetic properties. That's something very interesting. And so we will talk more about the applications of this in this short introductory session. So let's get started. Now, to understand magnetism, we should start from the beginning, not from the Big Bang, of course, but from the chemistry of the magnetic materials. So you must be familiar with the shells and orbitals. An electron shell is the outside part of an atom, as you can see in this image, around the atomic nucleus. And as you can see here, the shells are named from the bottom up, K, L, M, N, and so on. And every electron shell have one or more electron subshells, right? At the right, the figure on the right. And every subshell may have a few orbitals, as you can see here. An orbital is basically a three-dimensional description of the most likely location of the atom, of the electron that spins around the atom. And magnetism, now we will see more about that, but magnetism is an element such as a metal that has the electrons configuration in that element is not evenly distributed, right? So you may recall from high school chemistry how the subshells are organized with respect to energy bands. I don't go into too much detail, but you see how they are organized in this image. Now, for example, if I were to write the electron configuration of an element, a metallic element such as iron, which has 26 electrons, I would have to say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6, and that's what you see here. And if I were to draw this configuration with respect to the energy bands and levels that you've seen here, um, it would look like this. And you notice that there is a subshell, 3D, that unlike the norm, the electrons are unevenly distributed. Um, and just for your information, D subshell is consisted of 5 orbitals, and since they are not completely filled, it means that there is a favorable direction of spinning of electrons. Now we'll talk about spinning in a little bit, right? So there are a few other elements, including iron, in the periodic table that have this property. Their D subshell is not evenly filled with electrons. And again, magnetism in an element such as iron is created by the uneven distribution of the electrons in these orbitals. So the irregular rotation or movement, rather, caused by this uneven distribution of electrons shifts the charge inside the atom back and forth, which that creates a magnetic behavior, magnetic dipole. Let's review the physics of magnetic materials a little bit before we jump into biomedical applications. Now, so picture a nucleus shown here in green. And there is an electron spinning around this nucleus. You may be familiar with the right hand rule, which is used to find the direction of a magnetic field orientation given the direction of the electron spinning around the atom. So in simple terms, in our case here, if we apply the right-hand rule, we get a magnetic moment upward from the nucleus, but the electron itself is spinning around itself. So there's another magnetic moment due to this, and sum is what we generally call the magnetic moment of the atom, the entire atom, right? Um, so if we think of a unit material or think of a very small element where the magnetic moments of this unit and the neighboring atoms are all facing in a single direction, that is called a magnetic domain. And this is a very key concept that I will be referring back to it. So make sure you understand this part. So in fact, all materials can be defined by the orientation of their magnetic moments and form various types of magnetism, uh, um, uh, ferromagnetics and ferrimagnetics and antiferromagnetics and so on. And this is all related to their magnetic domain. So this is a very small unit of a whole bunch of atoms that have similar magnetic moments, right? And these atoms are neighboring atoms and they have similar magnetic moments. Now, uh, let's talk about another interesting definition, magnetostatic energy. Uh, you surely have experience with a broken magnet. When we were kids, we used to play with magnets, and if they broke, they would not they would not quite stick together at the broken section of the magnet. That is because large magnetic materials consist of several domains, and that is in order to minimize the energy uh, in that material, which is the magnetostatic energy. As soon as your magnet breaks, the magnetic moments will rearrange themselves. So the energy would be minimized, right? So on the left, you see this giant magnet, and that is broken into two pieces, and it rearranged itself. So the magnetic flux that you see are no longer are smaller. And then if you break it still down to your right, you'll see that this magnetostatic energy is even reduced more. So this is what happens. You can think of each section as a domain, and in each domain, the magnetostatic energy is configured in a way that it would allow less energy consumption, right? Um, so, how do they arrange themselves? So, the boundary separation and what separates between the two neighboring domains that you'll see here is called domain wall, and and you can see that each domain contains a large number of atomic magnetic moments, but um, 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 uh, these are created by macroscopic current related to the spin of electrons, as we discussed earlier. And the way the magnetic moments would rearrange themselves to minimize energy, um, um, uh, the magnetostatic energy, in fact, that I discussed, is by changing their position and angle towards one another, right? You can clearly see this in this image. So these little spheres in the middle are the atoms, and so you have domain one and two, and between each domain, the the rearrangement happens in this way. So if you place um, a material, now if you place this material inside a magnetic field, the rearrangement doesn't always happen just by breaking down the material. If we place them inside an external magnetic field, the magnetic moments try to align themselves with the field direction. And as we increase the strength of the magnetic field, the external strength of the magnetic field, there are more and more domains that will be aligned with the field direction. And look, if you look at this image here, so if I have a strong magnetic field direction from left to right, obviously the fourth atom from the bottom that has an angle with the direction of the field, there will be enough energy for that magnetic moment to align itself. And so all of a sudden, domain one becomes one atom more, right? And it will be the, so the domain will be bigger. And as we increase the magnetic field, the domain will become bigger and bigger and bigger, right? So we can classify all materials based on how they behave in an external magnetic field. Here's again the right-hand rule. If we have a coil and we're running a current around that coil, we see that there will be a generation of a magnetic field, and you'll see the flux that are coming out of the coil. But um, um, with that, we can define magnetic susceptibility, which is the answer to how a material behaves in an external magnetic field question, right? Basically, we're saying, so how does this material behave in an external magnetic field? And that would be the susceptibility of that material. You see here the flux goes around a diamagnetic substance such as wood. But some other elements like lithium, for example, that are paramagnetic, the flux runs through them. And this is the susceptibility of these two materials is different. So if we put, say, iron, that we discussed earlier, in the coil, we get a, a boost of electric field, as if iron amplifies the field compared to when the iron is not in the coil, and there's just vacuum in the coil. And we can trace that. So if we have inductance versus magnetic field, we can trace how this inductance appear with different materials. And so this is how we can classify all materials, in fact. So diamagnetics, and those that are repelled by the magnetic field, they have no unpaired electrons, and therefore unaffected by the strength of the magnet, such as copper, zinc, silver, gold, marble, even water and glass. So these are diamagnetics. Now, paramagnetics are attracted by the magnetic field. They refer to the magnetic state of an atom with one or more unpaired electrons. And the unpaired electrons are attracted by a magnetic field due to the electrons' magnetic dipole and magnetic moments. These are like aluminum, oxygen, titanium, and iron oxide. Ferromagnetics are aligned with the direction of the external magnetic field, so that a net magnetization remains after even the field is removed. We all have done the experiment when we rubbed a big nail against a magnet, a permanent magnet, and it becomes magnetic for a while. And even if we remove the magnet, the nail becomes magnetic still. So iron, cobalt, nickel are ferromagnetic, and these are in this category. Basically, ferromagnetic, fer in fer in French means iron, and so ferromagnetics relates to iron. And we also have ferrimagnetic, which is similar, but when a magnetic behavior is seen when a material have their magnetic moments aligned with the magnetic field, but in an opposite direction, right? And that is a ferrimagnetic material. So all the materials can be basically classified to look like this, as you can see in this image. And there's a constant called mu naught, which is basically a relative permeability. And when you have a ferromagnetic material with a permeability way higher than permeability of vacuum, then You have ferromagnetic material and paramagnetics and diamagnetics and so on. And you see here a table of relative permeability numbers associated with some of the materials, such as vacuum, which is a non-magnet, and the permeability is 0. Then you have a diamagnetic like silver, which is around 1. Aluminum is about 1. It is a paramagnetic material. Then you have cobalt, nickel, iron with a really high relative permeability, and these are ferromagnetic material. All right. So how do we measure the response of the material in a magnetic field? One way is it was with a device called vibrating sample magnetometer (VSM), uh, and what it does is very simple. You put your sample at the tip of a rod. Usually, it's a glass rod, and the sample and a sample holder that is attached to that glass rod. And you place it inside a giant magnet that goes from 0 to a few Tesla, I believe, and then goes back to 0 and back to a negative few Tesla. And at the same time, the sample starts to vibrate at a specific frequency, and there are these little orange things that I put in this slide. These are the pickup coils around the sample that they pick up the changes in voltage as the external magnetic field increases from 0 to positive and then negative numbers. And the machine can translate this the change in voltage into the magnetization of the material, and how the material is magnetized in simple term. So here's what we get from this VSM, a curve or a loop rather, that is called hysteresis. As the magnetic field increases from 0, the magnetic moment starts to align, and eventually they will saturate, and they can no longer align any further, and that's all the way on the top. Once we go back to 0, and perhaps increase field in the other direction, to the opposite direction. But as you can see, there is a delay, just like when we rub the nail against a permanent magnet. There was a delay in losing the magnetization, and I'll explain this in the next slide. All right, so from 0, so if we graph this on the y-axis, you have magnetization, and on the x-axis, you have the field, the external field strength, right? So from 0, we start increasing the field strength, and the magnetic domain of the material becomes more and more aligned, as you remember in the other slide. So the domains are getting bigger and bigger. And as the domains are getting bigger, the material becomes more and more magnetized. That is when we reach number 1, right, in this figure. And then we increase more and more until we reach number 2, where the material is saturated. Now, all the magnetic moments are aligned with the field direction, and it's just giant big magnetic domain, right? Everyone is aligned. Now, this is what we call MS, magnetization saturation. The material can no longer be more magnetized, right? Now, if we decrease the field to 0, there will be some sort of magnetization left in the material, just like the example of the nail that I talked to you about, and that is MR remanence magnetization. That is where the field is zero, but you still have some sort of magnetization. Then we increase the field in the opposite direction, and we get to a point where the field is being applied at point 4 in an opposite direction, but the magnetization is zero because it's just trying to cancel out what it remained in the material from point 3, right? And we continue on that path and same direction when we reach number 5, which is again some sort of uh, uh, saturation on the other side. Now, the point where the field is applied but magnetization is zero is called coercive field. That's number 4, HC. That's coercive field, and it is very important. We'll talk about that a little more. So you have a width for this hysteresis loop from 1 HC, from negative HC to positive HC, and that is something that we'll discuss in later. But then from point 5, you go back to point 6, which is the negative, basically a negative MR, where you have the remanence magnetization on the other direction. Now, obviously, temperature of the material influences this hysteresis behavior of the material, and as temperature goes higher, it might lead to a diminishing of the hysteresis loop, as you can see here. The temperature where the hysteresis loop gets interrupted, say, is called Curie temperature, right? And these are some elements with their Curie temperatures. For instance, gadolinium is 16, nickel is 358 degrees Celsius, and something like cobalt is 1,117 degrees Celsius. And so the material, when it gets to that temperature, it will not exhibit this sort of hysteresis behavior, right? So you can also change the way the hysteresis looks like by using combination of core and shell materials. So you can see here, and if the core is a ferromagnetic and the shell is behavior, the looks of the magnetic behavior changes, right? And there's a lot of applications for this in the industry. So expectedly, the different materials have different shapes of the hysteresis loop. And one type of material that is particularly interesting for us, especially in the medical field, are the superparamagnetic particles. And they don't have a loop of hysteresis with the so-called lack of hysteresis, as they say in the literature. It just aligns. So the blue line is a hysteresis behavior of superparamagnetic nanoparticle. And it is super important because it does not retain, this lack of hysteresis means that it does not retain magnetization. So the way that happens is when we go very small in the particle. A typical example of that is iron oxide. As we said, iron oxide is a paramagnet. But if we go less than 20, 15 nanometers, they become super paramagnetic, and they will behave this way. And that is both exciting and important because, especially in the biomedical field, because if we use magnetic materials in the body, we do want to influence them remotely via an external field, say pull them around lesion or deliver some sort of drug with them. But we don't want them to stay magnetized once we remove the external magnetic field. So super paramagnetic nanoparticles are very important in the biomedical field as far as their application goes, right? And this is where I said the coercive field, the HC, the width of the hysteresis loop becomes important. And this is my slide before, I think, my applications. But um, um, we draw the coercive field width of the hysteresis with respect to the diameter of the particles. And if you remember, so if you're super paramagnetic, the diameter is 0, the size is 0. So that's where you have that straight line until your particle starts to be bigger and bigger with respect to hysteresis. The HC becomes bigger and bigger. And an interesting point here is the maximum peak of the coercive field, which is the borderline between and if a particle is a single domain or a multi-domain, as you can see in this image. And before that, it is basically super paramagnetic, right? All right, so how do we synthesize these iron oxide spions, super paramagnetic iron oxide nanoparticles? There are different techniques and strategies. Co-precipitation, thermal decomposition are brought here. With co-precipitation, you add Fe2 plus ion and Fe3 plus ion, mix them together at high temperature and the right pH, and usually between 9 to 14. And the particles precipitate at the bottom of the container, simply put. With thermal decomposition, basically you use a precursor and a solvent. The macro emulsion is another technique, and sol gel is also another technique that is used to synthesize iron oxide nanoparticles. I don't discuss them now in details, but you can definitely look to available literature online to learn more about how they are synthesized. Now, surfactant is an important concept. Once the nanoparticles are created, we use surfactants to keep them stable in our solutions and basically away from each other, because magnetic nanoparticles can stick together, and if they're not taking, if they're not taken, if they're not with the surfactant, and they will agglomerate and can cause difficulties. So these surfactants could be organic, like such as fatty acids and dextrin, for instance, or maybe other polymers, or inorganic, such as silica or silica dioxide, or even gold. Another important application of surfactants is that they can introduce additional binding sites to the magnetic nanoparticles for targeting or other applications. Now, we have synthesized our magnetic nanoparticles, super paramagnetic nanoparticles, and we have put some sort of organic surfactant to uniformly distribute them in a liquid, whether it's oil-based or water-based, doesn't really matter. And as long as the particles are uniformly distributed in the liquid. Now, this is has a name. This will be called ferrofluid, and it's a fluid that contains a lot of iron oxide nanoparticles or magnetic nanoparticles of the iron oxide type. And if it's well distributed, then by moving the particles, you can basically move the liquid width. And if you distribute it in oil-based surfactant, we can enjoy playing with them a lot. In fact, I have this little image or rather a clip. So these are oil-based ferrofluids, and that that he pours into the water and bring a strong magnet near. You can see right now that, yeah, you can see how the ferrofluid moves with the magnet, and it is very fascinating. And there are tons of these videos online. I invite you guys to take a moment and look online and just just say ferrofluid and magnets and on YouTube, and you'll see a whole bunch of experiments, and they're very cool. All right, so let's talk about their potential applications, magnetic nanoparticles. And you can divide their applications into a diagnostic section and a therapeutic section. And in this diagnostic section, we can discuss more. We can uh, uh, classify further in vivo and in vitro. And I think I'll explain just a little bit of how each work. So drug deliveries comes to mind when we talk about magnetic nanomaterials. The first application that actually everyone will think about, basically, if we incorporate the drug of interest with magnetic nanoparticles and inject them to a subject, in this case, it's a rat, by focusing a magnetic field in a certain location, we can see an accumulation of the particles along with the drug, and consequently, we can expect the majority of the drug to reach that certain location that we're interested in. Um, um, this is true for humans as well. A strong magnet can pull the particles to get trapped from a vasculature in a desired location. The only difficulty with this is that the target location has to be superficial. We cannot use this technique to reach deep locations in the body, although there are other techniques that we can definitely use to do. All right, so I'm going to go a little faster. So the magnetic liposomes, magnetic core, polymeric shells, nanoparticles, and magnetic hydrogels, magnetic missiles are all different types of are all different types of this magnetic material using in drug delivery. Same as aerosol nanoparticles, that we have aerosol nanoparticles that are magnetized, and by breathing them, whether it's a subject here, a rat, or a human patient, by breathing these aerosols that are magnetized, you can deliver the particles into the right location where you want. Right. All right. So hyperthermia is another very interesting topic with respect to magnetic nanoparticles. Basically, hyperthermia is elevation of temperature, body temperature. And once you elevate the body temperature around, say, tumor, you increase the susceptibility of that tumor towards other forms of therapy, such as radiation or chemotherapy. And once we put a magnetic nanoparticle inside a magnetic field that alternates of direction, we increase its temperature, right? So think of a magnetic nanomaterial. It goes in the middle of a magnetic field. It aligns itself with the it aligns its magnetic moment with the field direction, and then you change the field direction and it tries to align itself again with the field direction. Now, if there are two big mechanisms that are at play here, there's a Brownian mechanism that basically says that the magnetic particle itself turns to align itself with the field direction. And there's the Neal relaxation that basically is just the magnetic moment that switches to a different direction. Regardless of the mechanism, the material becomes heated, and this is fantastic, because if you have this material inside the body and the body goes under the alternating magnetic field, then you can increase its temperature remotely, and the temperature that is increased, then it can affect the area that you're working on, whether it's a tumor or a malignancy that you're trying to intervene. There's a company in Germany called MagForce. They are doing clinical studies on this technique, and the only problem is that technically it's very difficult to reach the required magnetic field with the frequency at the scale of a human. So when you look on the literature, most of the stuff are done with smaller animals, right? And this is a picture of their machine, and that's how a patient lies underneath. There will be some sort of magnetic material injected into the patient, and then the alternating magnetic field will cause the magnetic material to heat up, right? Um, Other applications of hyperthermia, um, 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 we can think of cryopreservation. This is a subject that I'm personally interested in. So when we freeze a tissue in liquid nitrogen, the rate at which the freezing happens is very fast, and that this this fast rate causes low creation of, or minimal creation of, water crystals in the tissue, and this will help with the actual freezing. But when we thaw the tissue, there's a problem with that, because the rate at which we are heating up the tissue, it's not uniform and it's not fast enough, and that causes the tissue to get damaged. And so the idea is to incorporate the magnetic material, magnetic nanoparticles inside the tissue, and then placing the tissue in the alternating magnetic field. And once you do that, the heat generated from the nanomaterial will help thaw the tissue faster and more uniform, right? There's also hyperthermia in neuroscience. So these people, they use the heat shock and heat shock proteins on neuronal cells, and by turning on the the alternating magnetic field, they were able to record action potential from neuronal cells remotely. So this is super exciting. This is another example. So this is a worm. As soon as they turn on the field, the neurons starts to fire. So the worm starts to walk in the opposite direction, right? So when they turn on the field, the worm starts to again walk in the opposite direction. The trigger controlled release is another technique. So there are these polymers called hydrogels. They're 90%, about 90% water. And the idea is that, so these hydrogels, when they can be electric sensitive, they can be pH sensitive, or they can be thermosensitive. If they're thermosensitive, if you increase the temperature, they collapse, sort of, and it's just like a sponge. They will release their water content, and their polymer chains will organize very neatly, and so there won't be any more room for water molecules. Now, the idea is that if you incorporate your drug of interest and magnetic nanoparticles, you send this capsule inside the vasculature. You guide it with magnetic field to wherever you want, and then if you apply an external magnetic field that is alternating, the heat generated on the magnetic nanoparticles will cause a collapse of the hydrogel, and thereby releasing the drug at the location. So that's another application. Now, with respect to the diagnosis, we have MR contrast agents. So basically, you know how MRI works. I don't think I have a lot of time to discuss that, but MRI is consisted of different fields, and basically, if the tunnel of the MRI is the field inside the tunnel of the MRI is super uniform, and so if you have a material inside that disturbs that uniformity, then your image will be disturbed. And that's why, for instance, in this image, this person has something on his head or her head, and so that part of the image is disturbed. Now, if we and that is why basically when you go into an MRI, they ask you to remove your necklace or your watch, because you don't want the field to be disturbed. Now, if you at the nanoscale try to disturb the field in the MRI, obviously the implication is larger, but it's not as much to disturb the entire image. But then what we can do is that we can coat the magnetic nanoparticle with some sort of drug or some sort of ligand, send it into the body, and then if there is a specific target the region, the nanoparticles can stick to it, and under MRI, that part of the image will be disturbed, and then we would know that something's going on in that part of the body. Right? Magnetic labeling, it's another application. Basically, you coat the nanoparticles with some sort of label. It could be CD63 or 1 or 9 or whatever, and you run them into your bit. They get attached to something, and then with a magnet, you can pull them aside, and you can do all sorts of interventions. Basically, this is done in microfluidic systems. Biosensors is a very nanoparticles, magnetic nanoparticles are used in biosensors a lot. Here you can, in A, you see a nanoprobe structure with a magnetic core and some sort of shell, and with ligands on top. And then as you and the way it situates itself in a liquid is specific, and then if it attaches to something, this the angle that it's situated in the liquid changes, and you can have a detector to detect that. Magnetic separation is another technique. You have magnetic materials that are linked to some sort of ligand, receptor, and then you can pull whatever you have with a magnet that is attached to them to a side. Transfection is another technique that you obviously transfection is sometimes troublesome because it is dependent on how a cell behaves. So sometimes some sorts of transfection may not completely work, So magnetic nanoparticles can help with that. You attach them to a nucleic acid or a drug, and then you pull them inside the cytoplasm of the cell to deliver your medication. Magnetotactic bacteria is what is very interesting. These are real bacteria that they generate magnetic nanoparticles inside them, and they align themselves with the magnetic field of the Earth. And they're all sort of played with them a lot during my graduate studies. And so these bacteria, what we did in a lab was to basically attach these bacteria with liposomes that are containing a drug, and they were guided towards a tumor, and they went inside the tumor, and they actually got into the necrosis site area of region of the tumor as well. Last but not least, the toxicity of the material is very, the magnetic material is very important. There are basically iron oxide nanoparticles is known to be non-toxic, but it is not very, I mean, the scientific community is divided to say if they're not toxic. What I'm trying to say here is to be aware of the toxicity of the material. Well, thank you very much for listening to this presentation. I don't know if there's any questions. I'm not sure how I can.
Okay, thank you very much, Dr. Tabatabaei, for very nice and interesting lecture. Actually, we have some question in the chat box. Maybe I will read the question. The first question is, after drug was delivered, what the next treatment needed, like how to secrete the spion, I mean, is it safe for spion to stay in long time inside the body?
Obviously, okay, so obviously the safety is an issue, but it's a compromise. I usually get that question. It's a very good question. The thing is, when you have a patient with a terminal brain tumor, for instance, and the expectancy, the life expectancy of the patient is about maybe 6 months or 3 months. So like in case of glioblastoma multiforme, the 27% survived the first year and 6% survived the second year. So it's very, so the having some sort of I don't know, whatever concentration of magnetic nanoparticles inside your body to increase your life expectancy or the patient's life expectancy is the key. So even chemotherapeutics are toxic, right? They're toxic to all cells. They suppress they're immunosuppressants, and so but you see if the benefit of the chemo outweighs its risks, and it's the same here. So do we see if the benefit of having magnetic nanoparticles to deliver something in the body or to work as a hyperthermic applicant, is the risks associated with them, is it worth it or not? So that's something that the physician can decide. But definitely there is toxicity to all sort of materials that you inject into a body.
Yes. Yeah, okay. The next question may be almost same question, but I will read the question. Beside positive innovation, have you measured the disadvantage or negative effect on body detection system whether these magnetic materials in nano accumulated, then cause a pollution in body defensive system. As Nano mentioned, our body cannot detect this material.
I'm sorry, I didn't follow this question. Can you repeat the question?
Okay. Besides positive innovation, have you measured disadvantage or negative effects on on body detection system? Whether these magnetic materials is in nanoscale, so it will be accumulated, then cause a pollution in body defensive system.
Right. So this is something that that I discussed just in the previous question. This is a great question. Yes, there are disadvantages to having magnetic nanoparticles inside your body. There are even disadvantages, in fact, of to have chemotherapeutics in our body. Now, in the in the um, uh, with respect to diagnosis, the magnetic nanoparticles that are being injected into the body is not as the volume and the concentration should not be as high, but nevertheless there is toxicity. There's always toxicity. Now, let's say in CT, you go in a CT and they inject you with material, a contrast agent material that is called Gatavist, for instance, commercially available. Sorry, Visipack. Gatavist is for MRI. So Visipack, they inject you with Visipack. Visipack contains a lot of iodine, and iodine can be toxic, right? They inject you with a viscous solution of iodine, right? So again, it's a compromise. If whether the harm associated with the nanoparticle is smaller than the benefits, that's something that has to be discussed before applying the particles into the body.
Okay, thank you for your answer. The next question is, beside the material specific, what parameters do affect a Curie temperature? Could we tune the Curie temperature using a nanotechnology concept?
I'm sorry, I didn't get that. I don't
Okay,
know. Maybe I can
maybe
read
you,
the.
yes, you
Yeah,
can read in the chat box.
yeah. Let me bring the chat box. Which one is it?
Uh, the last two question.
Okay, on behalf of my colleague, no. To control drug labeled magnetic nanoparticles to target site, how much external magnetic field is required?
No, the before that question.
Is it very good? It's a very good presentation of spions besides positive. No. Has nano dimensions or no. To all participants, if they have any questions, no. On behalf of my country, besides. What
Yes,
parameters do affect a Curie temperature? It's just a temperature. So you increase the temperature of the material. Could we tune the Curie temperature? Yes, in fact, you can by combining elements. As I showed you, gadolinium is at 16, and then there is iron at 500 or 700 degrees Celsius. So if we combine them together, we definitely can tune the Curie temperature. It's a very good question. All right.
Okay.
The controlled drug labeled magnetic nanoparticles to target site, how much external magnetic field is required? Depends on where you want to control them, where you want to take them. It all depends. And how to direct the magnetic nanoparticles to a site with a magnet. Now, if it's a magnet, you need a giant magnet. You need to take into account that there is there is a blood that is rushing into the macrovasculature, and it can affect the nanoparticles movement. So that's that. Is this possible that the magnetic nanoparticles or just nanoparticles be used on decision-making manipulation by delivering the nanoparticles to the brain? Yes, they can, but there's a big issue with the magnetic nanoparticles in the brain. So the toxicity can be amplified if they're in the brain. But there is a lot of literature about getting magnetic nanoparticles in the brain. You can look online for that. And the unique way will manipulate brain electromagnetic signals, then finally manipulate the thing. Yes, this is a very interesting point. I think Max Planck in Germany, the institute is working on something like that. This is something that a lot of people are interested to influence the magnetic behavior of the cells, the neurons, using magnetic nanoparticles. But this is not something that we've reached so far, but there is a lot of attempt for that. All right. So are we done?
Yes. Okay. Maybe if there are any other question from another participants, you can ask directly, maybe.
Yeah. So I'll put down my email address. You can ask me via email.
Yes.
All right.
Okay.
Thank you so much for the time.
Okay. Yes. I would like to say thank you too for your very nice and interesting lecture for today's lecture session. Um, so we really appreciate it. So maybe let's conclude our last session for today lecture. Thank you so much for your
All right.
attention.
Thank you.
Yes.
Bye.
Yes. Thank you.